So this was the first design of our robot. It was designed to have as much flexibility as possible in regards to the phone angle and just be a simplistic base that we could build from. Here we had adjustable container for the phone, which could be moved to any angle to allow the phone to face the ball and obstacles in its desired position. The inlets here were for the wheels, and the servo motors that drove the wheels sat on the platform. Around here was where the microcontroller sat and all the electronic circuitry. The inlet here was designed to cradle the ball. The maximum it could be, according to the small size league, was 20% of the area of the ball. This was our second and final design. The phone was actually positioned upside down and was able to see out this little hole here. It also had little ball stoppers here, so they were at the maximum they could be, and they were used to guide the ball when turning corners. Once again, the wheel inlets, we made them square though. The servos were once again positioned here, and the micro was still positioned at the back with the rest of the electronics. The batteries were also mounted on the top here. This is the final mechanical design of our robot in action. As you can see, the phone's positioned upside down and can see out here. We've got our ball stoppers, the infrared lights, the batteries on the back, and all the electronics are housed underneath inside. And here we've got our wheels. Our motors are obviously attached to them inside as well.
Hi, my name is Mirren, and I'm in charge of the electrical subsystem of this robot. So, with the goal of designing a cheap and efficient robot, the electrical subsystem was optimized to include only necessary components for its operation. As seen by the schematic, this system includes only a Bluetooth module for communication from the phone, a microcontroller to process and send this information to the motors, and infrared sensors for obstacle avoidance. The microcontroller used for this project is an Arduino Uno R3. While a microcontroller in general was implemented to help take the processing load off of the phone, the Uno was chosen specifically for its functionality to perform PWM for the motors, send and receive serial data, provide ease of programming through the Arduino program, as well as being able to be run off of 9 volts while also providing 5 volt outputs. Also, it is very cheap in comparison to similar microcontrollers. Additionally, it provided the functionality for analog to digital conversion used for the infrared sensors. These sensors, while not in the original design, were added to fix a navigation problem which arose due to the use of the potential field method. This method, which attributes forces to objects seen by the vision of the robot, allows navigation of the field by moving away from negative forces of the obstacles and towards the positive forces of the ball. This can be seen in the current simulation. And again, it can be seen in this practical demonstration. However, as this is a purely reactive method with no localization, this method is limited to the field of view of the robot and the reliability of the vision. Therefore, the infrared sensors were implemented as backup obstacle detection to avoid obstacles outside of the camera's field of view. This is done by an emitter-receiver device which reacts to the reflected IR light from the obstacles or walls. In effect, this allows for better maneuvering through obstacles in close range. This can be seen here.
The application is responsible for object detection, translation of pixel distances to real-world coordinates, navigation, dribbling, communication of driving commands, and also an overall game strategy is implemented in the application, which makes it possible for the robot to know when to search for the ball and when to search for the goal. The wall and the turf are simply detected by finding color blobs corresponding to the colors associated with the turf and the wall. The same is done for the ball, but an enclosing circle is also created around the contours of the ball blob. The radius in the center of the enclosing circle serves as center and pixel radius of the ball. The goal detection is based on color blob detection as well as edge detection.
When a canny edge filter is applied to the camera image, the edges of the goal are very clear. So the edge detection algorithm finds the start points and end points of these lines. The main advantage of this algorithm is that we can determine which direction the goal extends if just one of the vertical bars has been detected. In such a situation, the robot can move itself to a better position for scoring goals.
The obstacle detection is very similar to the ball detection strategy. The vertical edges of the obstacles are detected, and if both are found, a horizontal line is fitted between the two vertical lines. The length of the horizontal line is used for determining the distance to the obstacle. For this part, some calibration images were taken before from a known distance, and so when setting the real-world coordinates in real time, the pixel length in the current image is compared with the corresponding pixel length in the calibration image. The potential field algorithm was explained by Miriam, and so a list with obstacle coordinates as well as the coordinate of the target is sent to this algorithm. The output is a driving angle, and depending on its value, a turn left command, a turn right, a move forward or a move backwards command is sent to the microcontroller on the robot. This is done with means of Bluetooth.
The dribbling of the ball is entirely based on the position of the ball in the image. If the ball is too much to left or too much to right in the image, a driving command is sent to the wheels that will make the robot move a bit forward instead of keep on turning. This way, the ball will roll back to the center again and the robot can continue turning around.